Hello everyone, and welcome to the last video in solving the first problem related to the empirical energy models, which is concerning the FCC platinum, its Lattice constant, and its cohesive energy. We accomplished the first three requirements, and in this video we've covered the last four requirements here. So let's start by addressing this one. We are requested to calculate the to find the Lattice constant manually rather than using an automated algorithm like Newton-Raphson algorithm that's implemented in Go by adjusting the lattice parameter. Start with a lattice parameter of 3.7 angstrom. Take 10 points and plot the crystal energy as a function of the lattice parameter. This is a very, very fundamental plot, uh, which is basically energy as a function of volume. This is like a mechanical equation of state for the material. It's a very, very fundamental quantity. And in later exercises, actually, you learn how to extract some useful properties, some useful mechanical properties from this equation of state. And then the question is asking us to identify the equilibrium lattice parameter by the eye. So rather than an automated search algorithm, we will do this by the eye. Make sure to change the opti keyword to single because it wants me to calculate the single point energy at each volume. So I'm asked to vary the volume. So let's just think about this. Um, we are asked here to vary the volume up around 3.7 angstrom by taking 10 points. So maybe uh, uh, 5 points to the tensile zone and 5 points to the compressive zone or something like that. And I was asked to move in steps of how much does it say? This, yeah, of 0.05 angstrom, right? So that means I need to go like 3.75, 3.8, 3.85, and so on. And the same thing to the left, so I'll have 3.65 and I keep going to the left. And then I need to record the energy at each one of these lattice parameters and plot the energy of the crystal in units of electron volt versus the lattice parameter in units of angstrom. Or alternatively, I can also plot this versus volume. So it's the same story. And from this graph, I should get by the eye the equilibrium lattice constant. As you see, this is a manual procedure rather than an automated search algorithm, but its advantage, it generates a very fundamental graph that represents this material, which is the energy as a function of volume. Typically, this graph looks like this. Maybe allow me to adjust this for a second. Yeah, energy as a function of volume. Typically, it looks like this. Um, so there is some equilibrium lattice parameter, and it's the optimum one, which usually corresponds to the minimum energy. If we go to the right in the tensile region, or if we go to the left in the compressive region, either way, the energy will go up because you are getting far away from the preferred or the optimum lattice parameter. So as I said, this is a very fundamental graph, but here we will just deal with it for the first time, and all what we need to do is just to get the energy by the eye. So let's get into business. Of course, this procedure can be automated, and we will discuss automation in a later part of this course using scripts. But here, for first exposure, we will do this just by manual, by hand. So um, we can make a folder here. We can call it E underscore V, this energy versus volume. And you can copy the original file here for Lennard-Jones platinum. And we can copy for E versus V. And I can now, start organize my work. For example, I can create a folder with 3.7. So that's the 3.7 angstrom. I can create another folder 3.75 and so on and so forth. But let's just demonstrate the idea at 3.7 and see what will happen. It's very important that one has to be organized, having a folder for each lattice parameter. Otherwise, the output files will override each other. So in the 3.7, I will modify the input file. Instead of opti, I will make it single. Instead of 3.8, I will make it 3.7, 3.7, 3.7, and the angles will remain the same. Fractional coordinates, they remain the same as we discussed before. They are really independent. Um, since it's FCC symmetry, you don't need to change them, even if you change the last parameter. So let's save this. Let me check something. Yeah, so let's save this. And now we are ready to run this with gulp. So let's close, open a terminal, call gulp, software gulp version 6.2, oops, 6.2, gulp binary, and apply to the input file, which is platinum. That could give us an output, but I will call it out.3.7, just, to remind ourselves that this is the lattice parameter 3.7. And this is standard stuff. By the way, you could even just ignore checking it by simply grabbing the energy, and this will really will be part of our automation, or scripting, which we learn at the later part of this course. If I can grip this energy, it's minus 8.76 something electron volt. So that's the energy that corresponds to this lattice parameter. So in a sense, if I go back to my drawing here, we are done with the first energy that corresponds to 3.7, and that energy was found to be minus 8.767 electron volt. I need just to repeat this for all the other lattice parameters, and you can do this as straightforward as you see. Just change three numbers, the ABC lattice parameters, and we actually did this exercise. So let's summarize the outcome here. The outcome, we summarized it in this Python script, which we can also upload and make it accessible in the description of the video. So we actually surveyed the lattice parameters from 3.5 all the way to 3.95 in steps of 0.05. And then we calculated the corresponding energy. You see, the energy that we just calculated is at 3.7 was actually minus 9.765 electron volt. So we did these prior in preparation for this recording, and these are all the energies, and above you have all the last parameters in Python arrays, and we have some plotting lines here to help us to do the plot. So let's run the script, and here we go. That's the total energy of the crystal in electron volt versus lattice constant in angstrom. And as you see, it seems we surveyed a lot of the compressive zone. Meanwhile, in the tensile zone, there is only a small arm here, or a small part here. And with your eyes, if you can look by the eye, this square here at 3.9 represents the lowest energy, right? If the eye inspection is not good enough for you, you can actually inspect the numbers themselves here to convince yourself. And this is really close to what the software has obtained automatically. I believe the software gave us 3.911, right? But this is 11 you cannot get by VR. So yeah, so that actually answers this exercise. We varied the lattice parameter manually. And I think the exercise D in comparison to A, where we shows you how powerful and useful the utility, the automated utility to find the equilibrium lattice constant and its corresponding equilibrium energy. But in spite of this still there is an advantage or uses today for having this graph, the energy versus volume. As I said, it's a very fundamental graph, and later part of the course we will learn how to analyze it further. All right, so let's move on Part E. Part E requires me to repeat A and B, which is basically calculating the cohesive energy and the equilibrium lattice parameter but using the embedded atom potential input file. This embedded atom potential is taken from the 1990 paper by Sutton and Chen, and its link um, is cited here. By the way, this is not really the exact embedded atom potential. It's a very similar one. It's the Finnis-Sinclair potential, which is very, very similar to the embedded atom method. Really nothing new. We will just redo what we have done with Lennard-Jones, but maybe it's actually, we can actually close Spider now. We are done with this. So we can close Spider, as we will make this script accessible um, in the links in the description of the video. Let's go back and actually do the work with the embedded atom method. So I can make a folder, I can call it EAM, and I can copy the platinum.eam file here. Let's inspect it really quickly here. Pretty much the first block is the same, nothing new. Optimization, constant pressure, stress out. This is initial guess for the lattice parameter, and these are the coordinates of the atoms. But the new thing is this block. This is the block um, for the Sutton-Chen embedded atom method model for platinum. And by the way, I copied this block from Gulb library. So Gulb has a very nice libraries for some of the famous potentials, which you can use right away. This is not really the topic of this exercise, so we will not discuss it. But just what I have done here, I literally copied pasted this from the provided libraries of Gulp, right? And yeah, so as you can see, it also defines the species. It's platinum. There is a mini body term and it says what is type of EM functional that's used. It's a square root, and I hope the word square root clicks with what we have learned about the properties of the functional that we need to choose for the embedded atom method. There's an EM density power, some parameters. We will not actually delve into explaining these. If you are interested, you can check the manual of Gulp. But really what I've done here is I copied them from the library. And one last comment here is that there is still there is a pair potential in addition to the mini body term. If you remember, go back to the video where we discussed the embedded atom method for metals. There should be always some sort of a pair potential associated with the embedded atom method, and it's actually a Lennard-Jones potential, but it's not the standard 12 6. Instead, this is a 10 6. Okay, so we had a look at the file. Now we will go into the optimization. So let's call gulp again 6.2 and gulp binary platinum. Let's request an output which is going to be called out.eam. And it's very fast. So let's see what do we have here. Well, pretty much the standard output stuff, which we covered before, so there is no need to go over this again. And yeah, now one thing to notice, that there are two components of energy. If you go back to your Lennard-Jones calculation, there was only one component, the interatomic potentials. And in Gulp language, that's basically means the pair potentials, except for the coulombic, right? Because there's no coulomb here. The charge is 0. But then there is a mini body potential contribution, which is minus 44.2 electron volt. And the sum of these gives you the net total lattice energy. And then I guess after that, optimization will start. And in fact, also 2 iterations or cycles after the first one, an optimization has been achieved. And that's the final energy in electron volt. Um, and if we check the lattice parameters, they are actually 3.92. Of course, we still maintain the cubic symmetry. It's an FCC. The fractional coordinates didn't change. As I said, we are still maintaining the FCC crystal structure. But that's the equilibrium lattice constants, 3.92 angstrom. A little bit different than the one with Lennard-Jones. We will actually show a comparison table at the end. And that's of course the final density based on the embedded atom method. And yeah, it's still a fast calculation. Again, if you compare this with Lennard-Jones, not too much extra time. Of course, this is a little bit extra because there is the many body term and there is the pair potential term, the Lennard-Jones term, but still more or less the same time. It's not very expensive computationally. And if you look at the stress tensor, it's not perfectly zero. There is some numerical noise here in the normal components, the XX and YY and ZZ. But again, this is something very, very small. You might say, oh, come on, this is in gigapascal. But again, in atomistic simulation, when you have a small number of atoms, fluctuations of pressures are on the order of gigapascal. So when it is 0.00040 zeros and then 1 gigapascal, then it's really nothing from an atomistic simulation point of view. All right, so we can compute the cohesive energy as we learned last time, and the equilibrium lattice constant, just as a reminder, we'll do this quickly here. The cohesive energy is the total energy of the crystal with n atoms. That's actually the minus 23.4 minus n times the energy of a single atom. But then the energy of the single atom is zero, as we demonstrated in part 2 of these videos, and then divided by the number of atoms, which is 4. So all what you need to do is to take the minus 23.4 and divide by 4. In fact, we did this calculation here, and the answer is minus 5.86. So that's minus 5.86 electron volt, different than Lennard-Jones, and we will get to that in a second. So we are done with part D and E. Part F and G, we can combine them together. Basically, it asks you to go to literature and search for the equilibrium lattice constant and cohesive energy of platinum. And we recommend, of course, to rely on published work. But then part G is asking you to use a vanilla AI tool. Vanilla AI means it's not trained on databases of materials. It's a generic one, generic like ChatGPT or Google Gemini, and then also find out what they will tell you. So we can combine part F and G and in fact make some sort of a comparison table between among all the methods that we have used in this exercise. So this table summarizes the story. In terms of experiments, there is an old paper from 1928 in Zeitschrift Christographie, I don't know, I think it's German. So uh, uh, that actually reported a lattice parameter of 3.922 angstrom for platinum. In terms of cohesive energy, I found this reference, which is, I think it's computational work using density functional theory and quantum mechanics. And I think that's actually my bad. I don't recall if this is a computation. No, in fact, no. In this paper, I actually found a reference to another paper, which I should have cited, of course. Probably I can do this at the end of the video. That cites the cohesive energy to be minus 5.85 electron volt. So these are the experimental and the lattice constant. Now, if you compare them with Lennard-Jones, which we have calculated before, Lennard-Jones gives you a very similar lattice constant, 3.911. And in fact, that's the reason for this is that the potential was fitted to reproduce this property. Meanwhile, in terms of cohesive energy, it was not fitted to reproduce the cohesive energy. That's why it gives you a completely off cohesive energy. It's very, very far away answer, the minus 2.88. The potential was not designed to reproduce it. Meanwhile, the embedded atom method potential, even though it's an old potential, but it was trained to reproduce these two numbers. It was actually fitted to give the correct Lutz constant. As you see, it's very, very close to the experimental one. I think here there is a zero, right? There is a zero up to the third digit after the decimal point. And in terms of cohesive energies, was also fitted to reproduce the experimental one. Now let's quickly ask Gemini and ChatGPT in the prompt here. So let's start with Mr. Gemini. Hi, what is the equilibrium Lutz constant of FCC platinum and its cohesive energy? We can also take this as a copy to speed up when we ask GPT. So, all right, so it's reporting the correct, actually, it's reporting the correct cohesive energy, 3.92. Sorry, the Lutz parameter, angstrom. And the cohesive energy, it's just using the positive convention. So it's giving 5.84. That's quite good, actually. I think I recall in the past it was giving, a couple of months ago, I tried it and it was given some wrong answers, but now it's very good. So this is 3.92, and this is, I will put it with the negative convention here. Let's ask GPT. GPT, what do you think? The equilibrium last can be. All right, so it's given some answers. It's actually reporting some DFT values. And the experimental cohesive energy, very nice. And it's saying or claiming that density functional theory is reporting a range, which is kind of lower than the experimental one. All right, very good. I think this is quite impressive, I believe. So it's given 3.923. So let's summarize this. 3.923, and why this is large like this, and what was the cohesive energy is very similar to Gemini. So yeah, I think both AI tools were very nice, although they are not trained on materials databases, but they did a fair job, a very nice job, I would say, in this. Okay, so we are done with the first exercise. I hope you learned something, and see you in the next small series of videos related to the next exercise, which will be related to the vacancy formation energy FCC platinum. Thank you so much, and see you soon.